Welcome to lecture number 16 on measure and integration. If you recall, in the previous lecture, we had started looking at the notion of measurable functions on measure spaces. We will continue that study of measurable functions and their properties, and then we will specialize measurable functions on measure spaces. And then we will look at the space of measurable functions on when x is the real line and the sigma algebras are either Borel sigma algebra or Lebesgue sigma algebra. And if there is a time, we will start looking at the integration of non-negative simple measurable functions. So, let us recall what we had been doing. We had been looking at properties of measurable functions. So, that is what we will be continuing doing. Then we will look at measurable functions on measure spaces, look at Borel and Lebesgue measurable functions, and then look at integral of non-negative simple measurable functions. So, let us just recall what we had done regarding measurable functions. We had said that if x s is a measurable space and f is a function from x to r star, then saying that f is measurable, it is same as saying the inverse image of every interval I belongs to S for every interval I contained in S. And there were equivalent ways of defining measurability in terms of special intervals like this. This is same as if and only if f inverse of the intervals of the type C to infinity belong to S for every C belonging to R, and so on. So, and then we looked at what is called the algebra of measurable functions. We proved that if f 1 and f 2 are measurable, then f 1 f 2 measurable implies f 1 plus f 2 is measurable, implies f 1 into f 2 is measurable, and so on. So, today we will look at the properties of sequences of measurable functions. So, we want to prove the following, namely look at a sequence f n of measurable functions, then look at the function what is called the maximum of f n's. So, this is a function denoted by v n equal to 1 to infinity f n of x is defined as the maximum of f n of x n bigger than or equal to 1. So, this is called the maximum of the sequence f n, and similarly, we have the notion of minimum of f n's which is denoted by wedge 1 to infinity f n x equal to minimum. So, this is extra. So, that is the definition. So, claim is that if f n is a sequence of measurable functions, then the maximum and the minimum are also measurable functions. So, let us prove this. So, f n is defined on x to r star, and f n is measurable for every n bigger than or equal to 1. And we define the maximum n equal to 1 to infinity of f n of x to be equal to maximum of f n x n bigger than or equal to 1. So, this is the definition of this maximum, and we want to prove to show that this function v n equal to 1 to infinity f n, this is measurable. So, to prove that we can use any one of those conditions which we had defined earlier for measurability. So, let us look at maximum n equal to 1 to infinity f n of inverse of the interval. Let us look at say C to infinity. Okay. So, that means what? That means this is all x belonging to x such that n equal to 1 to infinity f n of x is bigger than or equal to C. So, To prove this, now we have to convert somehow this relation into individual f n's, because each individual f n is measurable. So, that seems this saying the maximum is bigger than or equal to c, that means at least one of them crosses over c. So, that is one way of doing it, but let us look at the equivalent criteria, namely let us look at the sets f n inverse, the maximum is less than or equal to c. So, that is equal to minus infinity so to c. Let us look at that. So, this is same as x belonging to x such that the maximum value f n x is less than c. Now, if maximum of something is less than c, then each one of them has to be less than c. So, that is the reason instead of using this kind of intervals, it is more convenient for the maximum to use this kind of intervals, because then this set can be written as intersection n equal to 1 to infinity of x belonging to x such that f n x is less than c. So, this is each maybe this may not be exactly true. So, let us take it this close, because maximum less than or equal to c, then every one of them will be less than or equal to c, that is okay. So, so we look at the intervals of the type minus infinity c closed, and that is intersection of these sets, and each one of these sets belong to the sigma algebra S, because each f n is given to be measurable. So, it is the intersection of elements in the sigma algebra. So, this set also belongs to the sigma algebra S. So, that means this proves the fact that the maximum of f n's is a measurable function. A similar proof will work for the minimum. So, let us look at the wedge n equal to 1 to infinity f n, that is defined as the minimum of f n x, f n x for n bigger than or equal to 1. So, claim is that this is a measurable function. So, once again for any c belonging to R, let us look at the minimum of f n equal to 1 to infinity inverse of some intervals, some type of intervals we want to show it belongs to S. So, let us try looking at minimum is minimum of this is bigger than c. So, let us try this. So, this is all x belonging to x such that the minimum of f n x n bigger than or equal to 1 is bigger than or equal to c. So, if the minimum of some certain numbers is bigger than or equal to c, then each one of them has to be bigger than or equal to c, because if even if one is smaller, then the minimum will become smaller. So, this is equal to intersection of n equal to 1 to infinity of all x belonging to x such that f n x is bigger than or equal to c. So, that implies, and this is nothing but intersection n equal to 1 to infinity of f n inverse of c to plus infinity, and each f n being measurable, this is a measurable set. So, it implies that this is a set in S. So, we have proved that if f n is a sequence of measurable functions, then we look at the maximum or the minimum of the sequence of these measurable functions, then that both of them are again measurable functions. So, as a consequence of this, we prove that the limit of measurable functions is also a measurable function. So, that is our next aim, to prove that the limit of measurable functions is also a measurable function. So, for that let us understand what is the limit of a function. So, let us look at a sequence f n. The sequence f n of functions, each f n is defined from x to r star. So, to define the notion of limit of f n at a point x, what we do is, for every x belonging to x, let us look at the maximum or the supremum of f n x for n greater than or equal to some stage m. So, this number the supremum that depends on m, and then we take the infimum over all m's. Okay. So, this is supremum, first take the supremums and then take the infimums. This gives you a function, this is called limit superior of f n at the point x. So, this is called the limit superior of the function sequence of functions f n x at the point x. Similarly, limit inferior of f n x is, so limit inferior is defined as you first take the infimums of f n x for n greater than or equal to some stage m, and then look at the supremum for all m bigger than or equal to 1. This is called the limit superior, and you must have seen in your elementary analysis classes that limit superior of f n x is always bigger than or equal to limit inferior of f n x. So, this inequality always holds, and the sequence f n x converges to f x if and only if limit superior f n x is equal to f of x is equal to limit inferior of f n of x. So, these are elementary facts from basic analysis about when is a sequence of real numbers convergent. So, it says that a sequence for any sequence of real numbers or extended real numbers, you can define the concept of limit superior, and also you can define the concept of limit inferior. Limit superior is defined by looking at the supremums of the sequence a n from some stage m onwards, and then this supremum depends on m. So, look at the infimum of all these supremums. So, that is called the limit superior, and similarly limit inferior is defined as first taking the infimums of the sequence f n x from some stage m onwards, and then looking at the supremums of these numbers which depend on m. And one proves that the limit superior of a sequence is always bigger than or equal to limit inferior, and the sequence is convergent if and only if the limit superior is equal to limit inferior. So, in case you have not come across these concepts, I strongly suggest that you pick up a book on elementary analysis and revise the concepts of limit superior and limit inferior. So, we are going to use that fact now here to prove that f is measurable. So, what is f? F of x is nothing but limit superior and limit inferior. So, why is limit? So, only thing to show is that the limit superior and limit inferior are both measurable functions, but limit superior of f n is nothing but first taking the supremums of f n x from n bigger than or equal to m, and then taking infimums m bigger than or equal to 1. And just now we have shown that if f n is a sequence of functions, then the supremums, the maximums are also measurable functions. So, this is a measurable function, infimums of measurable functions, that is a measurable function. So, this implies that limit superior f n is measurable, and similarly limit inferior f n is measurable. And saying that f n converges to f is same as saying this f is equal to limit superior f n or also equal to limit inferior of f n's. So, that proves the fact that f n converges to f for every point x implies, and f n is measurable implies f is a measurable function. So, limits of measurable functions are also measurable functions. So, this proves the theorem that the class of all measurable functions is nice, it is closed under taking pointwise limits. Now, let us observe that most of these properties hold for extended real valued functions also when properly defined. So, because only thing to observe is the following, that if f and g are extended real valued functions, and you want to define f plus g, care has to be taken, because f of you would like to define it as f of x plus g of x, right. But the problem comes if f of x is equal to plus infinity and g of x is equal to minus infinity, then what will be this number that is not defined, or f of x is equal to minus infinity and g of x is equal to plus infinity. Even then the problem comes, this number is not defined. So, what one does is to meaning saying suitably defined means look at all the points, call the set as A, where all x belonging to x, where either of these things happen, where f x equal to plus infinity, g x is equal to minus infinity, or f x equal to minus infinity and g x equal to plus infinity. Now, one observes that this set A is in the sigma algebra, okay, because f x is equal to plus infinity belongs to sigma algebra, intersection with that belongs to sigma algebra. So, all these sets, all this set A is in the sigma algebra. So, A is the set on which the problem can come. So, what one does is one defines f plus g of x to be equal to f x plus g x if x does not belong to A, and if x belongs to A, you can define it any number alpha if x belongs to A. So, with this definition it is easy to observe. So, let me leave it as an exercise for you to show that if I define it this way with alpha any value on the set A, then f plus g is S measurable. So, that is what I mean by saying that the above results, most of these properties hold for extended real valued functions also when those functions are appropriately defined. So, we will not go much into detail of this, one can easily verify these things. So, let us look at f and g to be another property of measurable functions is the following. Let us look at two functions f and g which are measurable, then the following holds. They look at the sets x belonging to x, say that where f x is bigger than g x, or the set x belonging to x where f x is strictly less than g x, or x belonging to x where f x is equal to g x, and similarly where f x is bigger than or equal to or f x is less than or equal to. So, all these type of sets are claim is are in the sigma algebra S. So, let us look at the proof of one of them and others will follow similarly. So, f and g are functions x to r star measurable. Let us look at the set x belonging to x such that f of x is strictly less than g of x. And so, our aim is to show that this belongs to the sigma algebra S. And since we are given f and g are both measurable, we are given the property that f x less than or equal to some real number is belongs to the sigma algebra, and similarly g x less than or equal to a real number belong to the sigma algebra. So, objective is try to interpret this set in terms of union intersections of something of sets of the type where f x is less than something and g x is less than something. So, for that we observe that for any x, if f of x is less than g x, then there must be a rational number in between them. So, for every x belonging to x, there exists a rational R such that f x is less than R is less than g x. So, here we are using the fact that rationals are dense on the real line. So, with this property we can write x belonging to x, say that f x is less than g x. So, this implies that x belonging to x, say that for some rational f x is less than R is less than g x, right, for some. And conversely, if for some R this is true, then obviously f x is equal to g x. So, claim is this is equal to union over R belonging to rational numbers. Okay. So, this is the only crucial point in this, that the set f x less than g x can be written as a union over all rationals such that f x strictly less than R strictly less than g x. And now, observe this set is an intersection. So, I can write it as R belonging to Q. This set is where f x is less than R and g x is bigger than R. So, it is x belonging to x, say that f x less than R intersection with the set x belonging to x, say that g x is bigger than R. Okay. So, what we have done? We have interpreted the set x belonging to x, say that f x less than g x as. So, let us just look at the set again. So, this is union over R. So, that is equal to union over R belonging to Q. What is this set? This is f inverse of f x less than R, that is less than R means it is minus infinity to R. And the second set is the nothing but g inverse of g x bigger than R. So, it is R plus infinity. So, this is the set f x less than g x is written as union over rationals intersections of these two sets. Now, f and g being measurable, this set belongs to the sigma algebra. G being measurable, this set belongs to the sigma algebra. It is intersection. So, the whole set belongs to the sigma algebra, intersection belongs to the sigma algebra, and rationals are countable. So, this is a countable union of elements in the sigma algebra. So, this belongs to the sigma algebra. So, what we have shown is the set x belonging to x, that f x strictly less than g x belongs to the sigma algebra S. So, that proves the first property of the theorem. Now, if we take just the complement of this set, so also implies that x belonging to x such that f x less than g x, the complement of this set, what will be that? So, that is all x belonging to x such that f x is bigger than or equal to g x. So, that set also belongs to the sigma algebra, right. And similarly, the argument which will similarly we said that f x less than g x belongs to it. So, let us write x belonging to x, say that f x is strictly bigger than g x is also in the sigma algebra, because by similar arguments I can write this as the union over all rationals of f inverse of so f x bigger than. So, that will be R plus infinity in intersection with g inverse of minus infinity to R. So, by a similar argument where we had f x less than, again we can f x is bigger than g x. So, there must be a rational in between. So, that must be true, and that will imply that this belongs to the sigma algebra. So, saying that f x bigger than g x belong to the sigma algebra is okay. And if you take the complement of this, that is nothing but x belonging to x, so that f x less than or equal to g x So, that also belongs to the sigma algebra, because this is the complement of the set in the sigma algebra. So, measurable sets have nice properties, namely if f and g are measurable, then operations involving measurable sets, measurable functions give you again sets in the sigma algebra. So, these are nice properties, and we will see use of these properties soon. So, with this we complete the study of measurable functions on measurable spaces.